Hello, am I audible?
Yeah, you are. Have you started the recording?
Yes.
Okay. Who will explain which question?
So I guess we can.
Hello.
Hello.
Yeah, who will explain which question?
I will explain A and B. Manikiran will explain C, and I think you will explain D.
Yeah, okay, sure.
Okay. So in the first question, we've been given a matrix of n rows and m columns, and each element is in the matrix is distinct. What we need to do is rearrange the elements of the matrix in such a manner that for every element A of ij in the matrix, this should not be equal to any element B of ij of the new matrix that we have created after shuffling. And if we cannot do this, we need to output -1. Otherwise, we need to construct such a matrix. Now, it is obvious when we can't do the reshuffling. This is when the matrix is of size 1 cross 1. So when we have a single element matrix, we obviously cannot shuffle the matrix in such a manner that for every index I and j, we have a different element, right? Now, let us take an arbitrary matrix of, say, suppose size 3 cross 2. So that's 1, 2, 3, 4, 5, 6. So we need to shuffle this in such a manner such that in the new matrix, the corresponding elements are not equal. Now, I think this can be solved in multiple ways, but what my approach was is we iterate over this matrix row wise and reverse the row. So 1, 2 becomes 2, 1, 3, 4 becomes 4, 3, and 5, 6 becomes 6, 5. Now, this is fine when the number of columns in the matrix is even, but it might be a problem when the number of columns in the matrix is odd. For example, if we have 1, 2, 3, 4, 5, 6, and if we reverse this matrix row wise, we get 3, 2, 1, 6, 5, 1. So you see that this number and this number is still the same, and this number and this number is still the same. So in my solution, which might be a bit overcomplicated, I'm sure simpler solutions exist. What I did was I first reversed the rows individually, and then I shifted all the numbers in the all the middle elements. So suppose let's take a 3 cross 3 matrix. So first I reversed the rows, and then I shifted these elements. In so this 2 goes here, this 5 goes here, and this 8 goes here. So we get 3, 8, 3, 8, 1, 6, 2, 4, and uh, we get 9, 5, 7. Now one final edge case remains. What if we have a matrix of size 1 cross m, where m is an odd number? So something like this, say 1, 2, 3, 4, 5. Now we cannot cyclic shift this middle element because there is no other element to swap this with. So my solution was simple. If we get cases like this, we just do 5, 4, 3, 2, 1, and just swap the middle element with the first element. So that's my solution for problem A. It's a bit lengthy. I'm sure simpler solutions exist, but this will do. Any doubts or any questions in this explanation? If you have any questions, you can ask in the chat or you can unmute yourself and ask me. No doubts. I hope this is clear then. Let's move on to the second problem. Okay, so in the second problem, we've been given a binary array. We've been given two binary arrays. What we can do, let's take this example, is we can choose some segment from L to R. Suppose we choose this segment, and then for every corresponding element starting from here, we just perform the XOR. and we replace that value with the value of the XOR. So suppose we take this segment from uh, 1, 2, 3, 4, 5, 6, 7. So if we take the segment from 4 to 6, we do A of 4 XOR A of 1. Then we do A of 5 XOR A of 2. Then we do A of 6 XOR A of 3, and so on. Finally, after performing these operations in an infinite number of times, we need to answer whether we can convert the string S to the given string T. That is the question. Okay, so let's try and solve this problem if in the given string we know that the first digit is a 1. So suppose let's take 101001, and we can take any other string, it doesn't matter what. So can we convert this string to this string using the operations as described in the question? So the answer is yes. Now what we can do is just consider this first digit. Since this is 1, we always consider segments of length 1, right? Now we need to make this digit, we need to convert that to a 1. So what we can do is just choose L is equal to 2 and R is equal to 2. So just this index. So 1 XOR 0 is 1. So we get 1. So this is what we get, right? Again, we need to toggle this bit and make this 0. So we take this, we take L is equal to 3, R is equal to 3. 1 XOR 1 is a 0. So this also gets converted. Again, we need to convert this index as well. So we just take this segment. 1 XOR 0 is 1. So we have this as well. Finally, what we can do is we need to make this 1 into a 0. So we just do L is equal to 1, R is equal to 1. So 1 XOR 1 is 0. So what we see here is that if the first index is 1, that means we can convert any string to any other string, 1 1 XOR any number basically toggles it. So if you do 1 XOR 0, you get a 1, and if you do 1 XOR 1, you get a 0. So this 0 gets toggled to a 1, and this 1 gets toggled to a 0. Right? Now, what happens if we have, if the number does not, if the string does not start from a 1, maybe it is 1 0, and then we get some random string. Okay, so now, as discussed, if we do 1 XOR something, say x, this number gets toggled, so it becomes x bar. 1 XOR 1 is 0, 1 XOR 0 is 1. It becomes the opposite number. But if we do 0 XOR some number, the number remains the same. 0 XOR 1 is 1. So 0 XOR 0 XOR x is just x. But 1 XOR x is x bar. Right? So suppose we need to convert this string to this string. Let us take subsegments of length 2, right? So suppose we need to convert this. So we will take this range. Now, if we take this range, this is L is equal to 1 and R equals to 2. So we have this digit becomes S of 1. Actually, let's use 1 base indexing, otherwise it gets confusing. So L is equal to 2 and R is equal to 3. So this bit becomes 0 XOR 1, because this XOR this, and so it remains 1. We cannot toggle this. But this bit we can toggle because 1 XOR 0 is 1, so this becomes 1. Right. So the intuition is this. So suppose we have some 0, 0, 0, 1 in the beginning, and then we have some other numbers, and we need to convert this to say something like this. If we take this segment and we do XOR here, so whatever we do XOR with these prefix zeros won't change the number below. Only this will matter. So what we can do is when we do the XOR here, this becomes 0, 0, 0, 1, and this one will become a 0. These will remain the same. Similarly, let's move shift this up a little. What if we do the operation here? So 0, 0, 0, and 1. Again, this will remain 0, this will remain 0, this will remain whatever it is, and then this will get flipped. Similarly, if we shift this by one index, so 0 XOR something will remain the same, this will remain the same, this will remain the same, but this will get toggled. So this gives our solution. What we simply need to do is count the number of zeros in the beginning for S before a 1 occurs. So suppose we have 0, 0, 1, right? We have two zeros in the beginning. So we cannot modify the first two numbers of the, we cannot modify the first two numbers. Otherwise, we can modify all of these other numbers. Similarly, if we have three zeros in the beginning, so we cannot modify these three numbers. But after that, any other number can be toggled. So finally, what we need to check is this. We have some S and some T. We count the number of zeros before the first one. Now, if for some index I, S of I is not equal to T of I, and I minus the number of zeros is not greater than equal to 0. So basically, if the first, these, suppose we have z is equal to 3, where z is the number of zeros before the first one. So if number of zeros before the first one digits from the beginning do not match, then we cannot form the answer. Otherwise, we can always form the answer. I think looking at the code be, will give you a better idea. Okay, this is just, I've taken input. This variable counts the number of zeros before the first one, and this is the why, this is the for loop which calculates the number of zeros before the first one. Now, if a of I is not equal to b of I, basically if the digits are not the same, and if I minus the number of zeros is less than 0, then the answer is no. Otherwise, the answer is yes. Uh, is this clear, or do you have any doubts for this question? If you understand, please give a thumbs up so that we can move on to the next question. If you have any doubts, I can explain. So you can. So feel free to ask in the chat. Okay. So I hope this is okay then. Manikiran, please explain C.
Okay. Okay. Am I audible?
Yes.
Okay. So in the problem, see, the problem statement is that
Yaroslav is playing a computer game, and at one of the levels, he encountered n mushrooms arranged in a row. Each mushroom has its own level of toxicity. The ith mushroom from the beginning has a toxicity level of AI. Yaroslav can choose two integers L, R, and then his character will take turns from left to right to eat mushrooms from the subsegment one by one. The mushrooms with numbers L to R. The character has toxicity level G initially equal to 0. And here in the computer game, you are given an integer x, which is the maximum toxicity level at any time. So, while iterating, if we eat a mushroom with a toxicity level k, and the following thing happens: the value of k is added to the current toxicity level of the character, and if the g value of g after adding the value of k is less than or equal to x, then the process continues. Otherwise, g becomes zero, and the process continues. Now, Yaroslav became interested in how many ways are there to choose the value L and R such that the final value of G is non-zero. Help Yaroslav find this number. So basically, the question says that you will be given an array and you need to find the number of subarrays in it such that let us assume that the subarray is from L to R. Now, what we will do is we'll move from L to R and add the elements one by one. If the current sum is less than or equal to X, we just continue. And if the current sum is greater than X, we will make the current sum is equal to 0 and then we'll move to the next index. So after iterating through the whole subarray, if the final current sum is not equal to 0, then that particular subarray is one of the subarrays of the answer. Okay, so the brute force technique is simple. We'll just iterate from 0 to n, and in the second for loop, we'll iterate from I to n, and then create a variable current sum and do all of these things. If you clearly observe in the brute force approach, every single index is a different subproblem. So what we are going to do is we are going to solve this using dynamic programming. So in the dynamic programming, define a we'll define dp of I as number of subarrays starting from I that satisfy the condition. So dp of I means the number of subarrays which satisfies our condition and has the left boundary of the subarray as I. So here simply the method is that we will iterate from the end because the subproblems are created from the end only. So if the idea is that if you are a particular index, let us say a5, a6, a7, a8, and a9, what we are going to do is if we are currently at a5, we find the first index where the sum of elements from the current index and that index is greater than x. Now what we are going to do is this is one of the subarrays which comes under our answer, and all the subarrays from let us assume that the sum of the subarray a5 to a8 is greater than x. Now the subarrays a5 to a7, a5 to a6, and a5. These three subarrays satisfy our requirements. Notice that we need to find the first index whose sum of the subarray is greater than x. So what we are going to do is I have first have taken the both the parameters n and x as input, and I have taken the array as input, and then I have created a map denoting to store the values of the subproblems, and I have created a vector to store the prefix sum, and I have calculated the prefix sum. Now dp of I denotes the number of subarrays starting at I that satisfy the condition. So I am iterating from the n, and the sum that we need to find is if the subarray is from L, L plus 1, and so on R, then the sum A of R minus A of L minus 1. must be greater than x. This is the sum we need. So the sum of a bar must be greater than a of l minus 1 plus x. If l is greater than or equal to 1, and a of r must be greater than x if l is equal to 0. So here I have did the same thing. Assigned a variable called sum and initialize it to x. If I is greater than or equal to n, I have added the prefix of I minus 1 to the sum. Then by using the upper bound function, I found the first index where the sum of that subarray is greater than x. Now the thing is that all the subarrays that start at I and end at idx minus 1, idx minus 2 and so on comes under our condition. So the number of subarrays from I plus 1, I plus 2, let us say the idx is the answer. Idx is the index where the condition is satisfied. So the number of subarrays is idx minus 1 minus I plus 1, which is idx minus I. So I have added idx minus I to our answer. And next, so the sum until idx is greater than x. Again, idx plus 1 is a new subproblem which we have solved before previously already, since we are iterating here from the n. So dp of idx plus 1 denotes the answer for the subproblem, uh, which denotes all the subarrays which start at the index idx plus 1 and satisfy the given condition. So if idx is equal to 1, which denotes the end of the array, which means that from the index I till the end of the array, the total sum is less than x. Hence, the all the indices which are in the range from I plus 1, I plus 2, and so on, n minus 1 comes under our answer. Here the number of indices is n minus 1 minus I plus 1, which is n minus I. So the number of subarrays is n minus I here, and if the index is not the end of the array, then we are idx minus I plus dp of idx plus 1, which is the next subproblem that we have already solved before. So at finally after this particular step, the dp of I denotes the number of subarrays which satisfy our condition and which has the left boundary as I. So we just simply iterate through the DP array and add all the values of each subproblem to our answer, and just we print the final answer here. Okay, is anybody having any doubts? Sidit Bhaiya?
Yeah, am I audible?
Yes, Bhaiya.
Okay. Is my screen visible? Can anyone say?
Yes, Bhaiya.
Okay. So let's move on to question number D. In question number D, what we have said is basically we'll do n minus 1 operations. So let's say n minus 1 operation. And in ith operation, we can add n edge. So we are given n vertices and we need to connect these vertices using n minus 1 operations. So basically there is a question and the constant on like adding the edges that we are also given an array A. This array A consists of values for each node and we can add an edge between two nodes, let's say U and V, if on ith operation, if the absolute difference of these two vertices modulo I is equal to 0. So this is our condition. So if we try to understand when will this condition hold? Like on what values of AU and AV this condition will hold? We can simply say when AU mod I is equal to AV mod I, then AU minus AV mod I will be equal to 0. So our main condition is this. Okay. Something also to notice is that n is up to 2000. So we can think something like n square. And yeah. So what we can do is what the value of AU mod I is what matters to us. So we can calculate these values for every possible I and for every node and store it. So it will be something like this. Let's say A1, A2, and like AN. And I will go from 1 to n minus 1. So 1, 2, 3 till n minus 1. So what we store is basically A1 mod 1, A2 mod 1, AN mod 1, and like that A1 mod 3, A2 mod 3, and like that it goes on. Okay, so our suppose let's take an dummy array, let's say 3, 7, 10, 12, and since there are four numbers, so there will be 1, 2, 3. If we calculate the matrix, it will be something like this: 1, 1, 0, 0, and 0, 1. This will be 1, and this will be 0. Okay. So this is not a very good example, but what we need to do is we need to check if two values have the same mod. Then we can do this on the first operation. Like in this case, we can see this 7 and 10. Basically, this is the first vertex, second vertex, third vertex, and fourth vertex. So we can see that second vertex and third vertex, we can add an edge between them on operation 3, and also we can add an edge between vertex 1 and vertex 4 in operation number 3. So if the values are equal, so then we can add an edge. So now the thing is, we also need to construct our tree. Since it is n minus 1 operation, so we will basically construct a tree. So okay, so how to construct the tree? There are many possibilities. Like we can take these two or these two. In here we can take these two or these two. So there are possibilities. So which possibilities we need to consider? Actually, in this question, we need to prove this using something known as pigeonhole theorem. So what pigeonhole theorem says is, if there are n containers and containers and m balls, and if m is greater than n, so one container will guaranteed have more than one balls. So that is pretty logical. So here also we'll use the same logic. So let's see it in a general way. So if we see there are n numbers, a1, a2, like an, and here 1, 2, 3 till n minus 1. Okay. So when we take mod with n minus 1, how many possible values it can give? It can give only n minus 1 values. So, and number of places where these values will get stored are n. So, by using pigeonhole principle, we can of course say that there will be, for some value of mod n minus 1, there will be two vertices. So basically, in this case, suppose n is equal to 5. Let's say 1, 2, 3, 4, 5. So there will be, of course, something like 1, 2, 0, 3. Since we are taking mod with 4, so one of the numbers will repeat. So it can be 2 or anything. So yeah. So let's say these two got repeated. So we can basically add an edge between them. It will be this, or there can be more numbers repeated. Okay, now the second thing comes. So in the worst case, here we have at least one pair which will match. When we move to n minus 2, so there are n numbers, again n numbers, and means you can think as n containers, and there will be n minus 2. Sorry, n minus 2 containers and n balls. So we'll try putting them. So what can be the case in the worst case scenario? Like it can be something like 1, 1, 1, 1, and 1, 3, or it can be something like 1, 1, 1, then 2, 2, something like that. Yeah. So it can be something like that. In either case, if suppose it's tree, let's think like we can maybe we can form a cycle as we go. So a cycle can never be formed. Why that is the case? There will always an answer possible because since here we can see 2 has got two values. So in the next case we can maybe think like here also the values get overlapped. But the thing is either there will be three values of 2, so maybe it is something like this, or it can be something like this, like 1 1. So we'll always have a pair other than the pair that we used before, so that guarantees us that we won't form a cycle. So yeah, so let's say we selected this, then we can select this, and we can directly move on like that. Let's go through the code. So in the beginning, we basically calculate this matrix or 2D vector we were talking about. We basically calculate all the AJ mod I. Then what we do is for each value of mod, we are taking it mod with I, right? So there can be values from 0 to I minus 1. So for each values of this, we store like for 0, which vertices are giving mm, 0 value, which vertices are giving I minus 1 value. Let's say node 1 gives 0, node 5 gives this. So here we basically are storing these vertices, which when modded with I will get the key. Yeah. And here we are taking j plus 1 to just to convert it into one base indexing. Okay. Now what we do is for each key or for each modded value, we'll check if there are more than two vertices in it. Because we must have like at least two vertices to add an edge, right? So if it has more than two vertices, then we need to check like something like this can happen. So let's say this vertices is taken and this vertices is not taken in the graph, so like in the tree. So yeah, so we need to add edge between them only when they are not previously connected. So to check this, what we can use is a DSU, or we can go for another method also, but DSU is the simplest. So basically here we check if if they belong to the same component or not. If they don't belong to the same component, we can simply pick it and simply break the loop. So yeah, that's the main idea. If anyone has any questions, you can ask, or if anyone is unable to understand.
But I can explain that MPP once more.
Yeah, sure. Let's take an example. That will be better. So yeah, we can take this one. Okay, yeah. So this was, I guess, one of the given example, maybe. So yeah, 99, 7, 113. So for this, what this MPP is storing, like this MPP has a key, which is basically the modded value of each vertices. So let's say AJ mod I. Yeah. So for each vertices, when we mod it with I, the value we are getting, we are storing it as a key. And here we are keeping a vector which basically stores the vertices which give this key. So in this case, if we see for operation 3, suppose like when we mod it with 3, when I equal to 3. So we can see like 99 mod 3 is 0, 7 mod 3 is 1, 1 mod 3 is 1, 13 mod 3 is 1. So yeah. So in this case, MPP of 0 will just be like this is vertices 1, vertices 2, vertices 3, vertices 4. So it will be 1, and MPP of 1 is 2, 3, 4. So basically what we are storing here is the vertices which when modded with I will give us this value. So that's the main thing about MPP. And why we are storing this is basically to pair the vertices and form an edge between them. As I said, is this clear? Why a cycle will never get formed? and why the answer is always yes.
Yes, it is clear.
Yeah, okay. So as we can understand, like the answer will always be possible. So basically, the answer will always be yes, and this a cycle will never get formed. We'll always have a choice where we can form a tree. So by doing this, we are keeping track of the vertices which we are gonna add an edge between. So to check it, basically, we need to store this here. Is there any more doubts?
No,
Anyone else having any doubts regarding this? The main funda of this question was proving that by just picking the vertices, the answer will always be yes. So for that, we needed pigeonhole principle to prove it. Or the rest was pretty simple only, I guess. Okay, if no more doubts, then we can, I guess, wrap up. Sohail, are you there? Yeah, yeah.